Hi, everyone. Good morning, good evening, good midday, good lunchtime, good night for all of you across the world who are here. I am very honored to be here, and I'm really excited to share with you, hyperspectral, which is really, really exciting. It's a really neat technology in the commercial space. And so, yeah, let's get started. So I'm going to talk about hyperspectral imagery for vegetation management for wildfires. That's going to be the focus. And a little bit about me. Hello, my name is Ellie Jones. I'm machine learning and data science lead at Wyvern. I'm coming to you from Calgary, Alberta, Canada. We just got 15 centimeters of snow overnight in April, which is just fantastic. I mean, it's good for the wildfire season, but maybe not so good for, enjoying the weather. I'm a bit of a data nerd. I've been working for about 5 years in machine learning and data science. Spent some time working on wildfire projects in Western Canada, and I'm really passionate about building really, really cool stuff. I just want to make a note here. My expertise is in machine learning and remote sensing. You folks in your local areas with intimate knowledge of local ecosystems and the forests, you're the experts here. And taking your expertise, adding Earth observation data is where good things happen. So there's a couple of key points I want to sort of drive home here. It's really difficult and it's costly to really accurately map forest types, vegetation species, health, fuel on a large scale. And another really big one is that traditional remote sensing technologies, can't really sense forest damage agents like, bark beetles until changes are visible to the naked eye. And so these are two really big things that hyperspectral can help out with. I'm not talking about just Wyvern, hyperspectral from lots of different sources is really, really useful. And so I think it's important to sort of go back and, think about forest fire danger, forest fire weather. This is a Canadian forest fire danger rating system. Every jurisdiction is going to have a different one. But let's look at our inputs, right? Our inputs are weather, topography, fuels, and ignition sources. Unfortunately, not yet. We can't control the weather. We can't control topography, and we can't really control ignition sources. I think lightning is probably easier to predict than humans, unfortunately. And so where does that leave us? Well, it leaves us with fuel. And fundamentally, having a better understanding of your forest composition, better understanding of your fuel and your fuel types is key to improving your response to fires and mitigation of risk. And so that's where we're going to be focusing today. So to categorize fuels, we do vegetation mapping, right? And so what are those current methods that we use? Well, we can send humans out, whether humans are, forest fire folks or, loggers or people actively working in the forests. Very, very accurate, extremely accurate, but, it's expensive. Humans are expensive, and unfortunately, we're pretty slow and we can't cover a large area. Then we go to drones and aircraft, which are, super accurate still, a little expensive still, less slow, but still, you're not capturing an entire province or a state in a couple of days. You're capturing, an entire province in a year or two. And then sort of our other option is satellites, remote sensing, traditionally less accurate, cheaper or free, which is fantastic, and fast and large coverage. And there's a really key trade-off between accuracy, cost, and speed. And so I'm gonna make the case here that, hyperspectral is gonna, support that and improve sort of that trade-off with satellite imagery. In terms of remote sensing technologies, there's a couple at play. Two groups are passive and active sensors. You have electro-optical, which are passive sensors, essentially a camera, measuring the amount of light being reflected off the Earth's surface. That's what hyperspectral is, the blue box. And then you've got active sensors like LiDAR, which sends laser pulses down, measures the amount of light returned, which is really, really great for understanding height, but also forest structure, including the understory, which is exceptionally cool. And then synthetic aperture radar, also fantastic, for measuring the shape and structure of objects. And, I think hyperspectral is a fantastic data source. LiDAR and SAR are also fantastic data sources. Merging them makes something even more incredible. And so this leads us into what is hyperspectral imaging. And so hyperspectral imaging is a passive sensor, but instead of measuring maybe, red, green, blue, near infrared, you're measuring sort of contiguous small slices across an electromagnetic spectrum. And from that, you can start to infer properties of the scene and the objects within the scenes, including chemical composition. And in terms of vegetation, we're measuring pigments, chlorophylls, carotenoids, anthocyanins, we're measuring those relative ratios and sort of, plant phenotyping and understanding sort of the cycle of vegetation. And so I think the best way to understand this is visually. Let me take a sip of my coffee here. So to compare against multispectral, our satellites there on the top. There's a lot of different hyperspectral satellites out there. Ours sense in the Venier range, most sense in Venier and SWIR, but you can see that we sort of image very small slices across the spectrum from 450 nanometers up to 900 nanometers, whereas multispectral satellites like Sentinel-2 measure sort of usually wider wavelengths, wider widths, and they're not contiguous, right? So you're missing out on data in certain spectrum parts of the spectrum, which can be really, really useful when you're trying to speciate or understand your vegetation. The other thing to look at here is ground sample distance resolution. Sentinel-2 is at 10 meters. Some of their bands are at 20 meters and 60 meters, and so those are great for sort of stand level statistics and understanding large groups of trees, whereas higher resolution is better for identifying specific trees, specific groups of trees, and so on and so forth. And I want to sort of sit on this plot for a little bit of time. This is, it's not directly applicable because it's crops in terms of vegetation, but I think the information is still there. So this is a plot of different spectral curves over the visible to near infrared and also shortwave infrared spectrum range of different crops. And so you could translate this into different species of trees as well. In the left-hand side, in the bottom, you're looking at the Venier spectrum. And from there, as I talked about, we're measuring pigments, we're measuring the relative abundance of pigments, we're understanding nitrogen use, light use, biomass, and plant stress and senescence. As you move into sort of SWIR and the infrared section, you're starting to understand leaf area index, you're starting to get into water within the vegetation. And I think what's really cool is being able to measure lignin, cellulose, and plant litter, especially for those dried and cured grasses. Being able to actually measure that is really, really, really important and cool. And so what's another fantastic thing that we can do with hyperspectral? Well, it's vegetation speciation. Because we collect so much more information in the spectrum, we can start to understand very subtle changes in reflectance in certain areas of the spectrum. Due to the fact that every species of tree is going to reflect light slightly differently due to different composition and different structure within the leaves. One study found that hyperspectral imaging can improve accuracy of speciation models by over 20%. I think if you look at the plot on the right-hand side, this is one area in the Bow Valley in Alberta, and we've selected a couple of different species of trees. Aspen and poplar, kind of similar. Spruce and pine, a little bit similar as well. And you can see with the Sentinel-2 image in that spectra, you're kind of struggling to differentiate between the different species. And when you collect more information around that spectrum, those species start to delineate themselves, and you can see on the Wyvern plot there, we're getting a lot more information, and that helps with speciation. And so what does it mean, speciation and forest structure and forest fuel types? Well, the more accurately you can map fuel types, the more accurately you can map your forests and understand your forests means more accurate weather and behavior modeling, ultimately improving response outcomes. And here's a good plot of some hyperspectral data in action. This is from the University of Alaska, which is fantastic. And so there's the Landsat Landfire product on the left-hand side, and they determined that the area that they were looking in, that Landsat product, isn't particularly useful, and it's also fairly coarse. So they used a Virus data, which is sort of an airborne hyperspectral system, and retrained the model and got really fantastic accuracy, especially looking at open and closed types of forest, which is really, really, really cool. The other thing I want to touch on is forest damage agents and vegetation health. About 5 years ago, mountain pine beetle was a very big thing here in Western Canada. Bark beetles are a big thing across the world. Let's take a segue here to sort of understand the bark beetle life cycle. In the first year, bark beetles will bore into the bark of trees and lay their eggs. Those eggs will pupate, and they will overwinter in those trees. And so for the first year, those trees look green. They're called green attack, and you can't really visually determine anything about those trees. You can't see that there's an infection or that they're dying. And then in the second year, those bark beetles overwinter and then exit the tree and go find new trees to infect and kill. And so only in that second year are you actually seeing any visual changes to the foliage. They're turning red and orange. They're visibly dying. But the problem is, you're actually seeing them visibly die after the beetles have gone and moved to other trees. And if there's high wind, they're spreading, and you don't know where they're spreading unless you physically go in and look at every trunk of every tree in a forest, which is, pretty impossible. And so in that first year in green attack, there are changes to stress pigments and moisture within the leaves, within the needles, and hyperspectral imaging enables pre-visual identification of bark beetle and other damage agents, and on a larger collection scale than if you were running drones or aerial imaging. So it does have some really seriously good potential for sort of mapping and understanding forest damage agents. And that turns into, action. If you can detect those damage agents early, if you can control infestation spread, you can mitigate risk. You can get those forests logged, get some money out of it, or update your maps and understand the forest better. There's a lot I could talk about here. Hyperspectral is a bit of a rabbit hole, and there's studies on every countless type of vegetation and every countless use case. And I encourage you to look up some studies. Hyperspectral imaging has been studied for the last 20 years. There's been fantastic papers and fantastic research around it, but we're at a point now where hyperspectral imagery is here right now and it's accessible to folks. I do have to plug my own company. But we have our open data program at opendata.wyvern.space. We also have a little knowledge center to understand more about hyperspectral imaging, some use cases and how to use our data. But there's also other fantastic missions out there. Nmap provides open and accessible data. Prisma, there's a couple American missions. Avirus is also incredible because Avirus will give you really detailed and rich spectral information at a very high resolution because it's an airborne product. Nmap also puts out HyperEDU for some more information on hyperspectral sort of education and background. And they actually have Nmap Box, which is a QGIS plugin, entirely free, that you can work with hyperspectral data in. So the sky's the limit. I'm very excited to be showing this off and talking to you about it today. Please feel free to reach out and connect with me. I'm on LinkedIn, and there's my email if you want to send me an email. Happy to chat wherever, and excited for the questions. Thank you all for listening to me talk, and